Yeah, thank you. I hope everyone can hear me. So I too changed the title of my work a little bit. I first want to start with actually acknowledging my collaborators from UWA and from the Helmholtz Zentrum, Dresden-Rossendorf. I'll start with a short introduction into hydrogen. Hydrogen has become a little bit of a buzzword in the fight against climate change. Here, as an example, are some newspaper headlines. They were all published within 1 week of each other, and they all were published within the last month. And why is hydrogen in the spotlight right now? Well, hydrogen could be a solution to decarbonize the hard or expensive to decarbonize industries. Which are those? We are talking, for example, long-distance transport. We are talking railway lines which are not electrified so far, and we are talking the fabrication of steel without coal. Hydrogen is going to be a thing. However, hydrogen gas sensing is actually not new. That goes back quite some time. However, the current commercial sensors are not quite up to the task. The current sensing techniques, for example, don't cover the full concentration range from near 0 to 100%. They typically use 2 sensing techniques to cover the whole concentration range, and this commercial sensor shown here uses, for example, a capacitive measurement and a resistive measurement on a nickel-palladium alloy. And you see, for both those techniques, you apply a voltage in the hydrogen environment, and then is possible yet small fire hazard. And also, these sensors are a typical response time of about 1 minute, and we just think that could be faster. What we would need is a sensor which is inherently fire safe and which can detect this broad hydrogen concentration range. Instead, I want to present to you the magnetic hydrogen gas sensor. Our group has proposed this sensing technique quite some time ago. I don't have the time to go too much into the details, so I will just present our latest research, and I hope I can explain its working principle on this example. Now, the make or break of any hydrogen gas sensor is the sensing element. In our case, this is a cobalt palladium rectangle shown there in blue. It's 30 micrometers long, 20 micrometers wide. Basically, when this cobalt palladium is exposed to hydrogen, its magnetic properties change. So that's why we call it the magnetic hydrogen gas sensor. In the alloy, the cobalt is responsible for the magnetic response, while the palladium makes it sensitive to hydrogen. And because the composition is so important for this alloy to work, I want to talk about fabrication and how we fabricate this alloy. We use a technique called bias target deposition, and we have equipment at the WA node of ANFF to use this bias target deposition, and that machine is called 4-wave. 4-wave, I show there the inside of 4-wave is basically a vacuum chamber. It contains 6 material targets, and on the far end is basically an electron gun and an ion source, which together build a plasma source. And you can imagine the substrate would be on our end, built into the lid, which is currently open. And the whole assembly is basically a hexagon-shaped prism with the plasma source on one end and the substrate on the other end. On the right-hand side, I show you how bias target deposition works. So we have a plasma source. This plasma source is emitting a very low energy plasma. And the ions in this plasma have very little energy so that they don't damage the chamber or they don't sputter away any material. The target from which we want to deposit material is then biased with a bias voltage. And when the ions come close to the target, they get accelerated, they gain momentum, they gain enough energy to actually sputter away from the target. The material that gets sputtered away flies through the chamber and lands on our substrate. Now in 4-wave, we typically apply this voltage as a pulsed DC voltage, and because in 4-wave we can control up to 4 targets at the same time, we can apply this pulsed DC voltage up to 4 targets at the same time, and we can control the bias strength and the pulse duration. We can fabricate any arbitrary alloy with up to 4 constituents. Now we come back to the hydrogen gas sensor. How do we probe the magnetic properties of this cobalt palladium strip? We use a technique called ferromagnetic resonance spectroscopy. And very, very simplified, at ferromagnetic resonance, magnetized ferromagnet, so the cobalt palladium alloy, will absorb microwave energy at a specific microwave frequency. And that microwave frequency is given here on the right-hand side. It depends on the material parameter, which, for example, could be dependent on the cobalt content in our alloy, and on the magnetic field which we apply to magnetize the ferromagnet. Now, when this cobalt palladium alloy absorbs hydrogen, its material parameters change, and because we fix the microwave frequency, that means the resonance occurs at a different magnetic field. We supply the microwave energy to the cobalt palladium alloy using that waveguide shown there. That waveguide is a microwave microresonator. And I just want to acknowledge the people from the Helmholtz Center in Dresden-Rosendorf, because they came up with the idea. They fabricated this resonator, which is actually deposited on top of our cobalt palladium alloy. Now, how is that exactly fire safe or fast? Well, our technology could be fire safe if we imagine it like that. We have the waveguide, which contains the microwave current that produces our magnetic field, which ultimately drives our ferromagnetic resonance. Microwave magnetic field can penetrate insulating materials. So you can imagine that as the vessel wall of a hydrogen container. However, the microwave magnetic field is completely shielded by the cobalt palladium thin film, so nothing of that microwave magnetic field actually penetrates the hydrogen vessel itself. So we can completely separate all the active elements, so the waveguide, from the hydrogen environment. That makes it very fire safe. And why do we think it's fast? Well, microwaves work in the gigahertz frequency range, so that's fast by itself. And the hydrogen diffusion speed in cobalt palladium is between 15 and 70 nanometers per second. And our typical thicknesses for our thin films is about 50 nanometers. So we should get a response within a few seconds. Compared to the commercial sensor, which I just said was the response time of about a minute. Okay, now we use the resonator. Why do we use that resonator? Well, with the resonator structure, we create a standing electromagnetic wave. The magnetic field is what drives our resonance, and with that standing wave, which occurs just under the cobalt palladium sample there, we create a much stronger magnetic field for a given microwave power than when we just use a normal strip line with a thin film on top. And we see that nicely here on the right, where I show FMR spectroscopy traces for the resonator with a much larger signal than for the thin film. How do we sense hydrogen with that? As I said, when the cobalt palladium absorbs hydrogen, the resonance condition change. So I'll show here on the left-hand side a nitrogen and the hydrogen trace, and we see that they occur at different fields. And this is concentration dependent, so if we don't measure in pure hydrogen, the resonance would occur somewhere in between those two curves. And on the right-hand side, that is a little bit more application-driven. Here we measure in a time-resolved manner. How do we do that? We set the magnetic field and the microwave frequency, which we apply to a fixed value. We then use a PID loop to control the magnetic field. So we control an electromagnet with a PID loop. And when we absorb hydrogen, the resonance shifts, and we set the PID to just keep the lock-in voltage at the same output signal. And we then measure the magnetic field and use that as a proxy of the hydrogen concentration in the environment. And we see here very nicely how we can differentiate between 5, 10, up to 100% of hydrogen. Now, to finish off, a quick outlook. We still need to work on the fire safe and fast. These have been mostly concept. We have shown in other research that it is possible to go fast to be fire safe. However, we haven't actually shown that it can be combined into one principle. And if you pay very close attention, the research I just showed you is neither fire safe nor very fast. And however, our next focus is actually more towards prototyping. We've received some funding by Woodside to basically get the laboratory-sized sensor, which you see on the left, down to something which is more the size of a briefcase. And I'm very glad that with the funding, I will be able to still access the ANFF network and hopefully make this work succeed. With that, I'd like to thank you for your attention, and I'm open for questions.
Thank you, Thomas. Really interesting presentation. And I actually was wondering if you have already tested the hydrogen sensor under a bit more challenging conditions, you know, in air or against potential interfering gases that could, you know, give a similar response to what you see for hydrogen.
No, we haven't gone too much into that. So we tested our sensor for the response of hydrogen in dry air compared to nitrogen. You don't want to go too high there because it becomes quite dangerous or possibly explosive, of course. Typically, our sensor will respond very similarly in air. We haven't looked into, let's say, poisoning of palladium with hydrogen sulfide or so on. There is research out there which looks at that, but we haven't tested our sensor for that.
Great, thanks, Thomas. Savanka is asking, how did you calculate the hydrogen diffusion speed?
That was actually not us, that is from different research. It's a very interesting research. They used an optical method, they did microscopy on it and had a transparent window over a cobalt palladium alloy so that the hydrogen was only absorbed on one end of the cobalt palladium film, and they could look through that glass window how it progresses, and they calculated the diffusion speed from the hydrogen front, basically.
Thanks, Thomas. Abu is asking, does this sensor work at room temperature?
Yes, this is all at room temperature.
Right. And then we have a question from Marius, who is asking if there's any interference to oxygen or humidity.
Again, there might potentially be. We haven't looked at that. Typically, with palladium-based hydrogen gas sensors, they work better in dry conditions, yes.
Okay, so Matt is asking along a similar vein, if the sensor is cross-sensitive to non-hydrogen gases. I think you've answered that question already, right? Last question from Marius. What temperature ranges can your sensor work across?
We haven't exactly looked at that, and it depends a little bit. To be quite honest with you, that research which I just shown is quite temperature sensitive. So your signal, or if we translate it into a hydrogen concentration, you would get an error of about 5 to 10% in the temperature fluctuation of your day. So that's something we will need to work on. That's part of what we agreed with Woodside to work on in our prototyping to make it more temperature resistant.
Awesome. Thomas, thank you so much for your presentation.
Thanks.